Hello, my name is Bo James. Welcome to my Research to Practice presentation for EDUC 5404G. The final product that I developed for assignment number 3 is a course outline with accompanying support documents. In this presentation, I will provide an introduction to the post-secondary discipline that I teach. I will then continue to provide background on the specific topic of my course outline and discuss the connection between the outline and an industrial need to educate technical personnel for employment. An explanation of how research has informed both the learning environment and course learning outcomes of the course follows, with an opportunity for viewers to provide me with constructive feedback. I primarily teach in a discipline known as Electromechanical Engineering Technology, or EMTY for short. EMTY is an advanced college diploma program that specializes in the electronics programming and mechanical technologies used in industrial automation, instrumentation, and robotics control applications, as shown in the laboratory equipment photos that students utilize at our college, found on this slide. In their graduating semester at Durham College, EMTY students are enrolled in a capstone course titled Supervisory Control and Data Acquisition, or SCADA for short. According to Bentley Systems, a SCADA system is a computer-based interface that permits operators to remotely monitor and control field-mounted equipment from a centralized computer location. SCADA systems are prevalent in building automation, manufacturing, oil and gas, power generation, and water treatment industries, to name a few. The first course learning outcome included in this SCADA outline requires students to identify the fundamentals of a SCADA system before beginning to develop one using industrial software. This infographic illustrates the purpose of a SCADA software package when applied to a water treatment application. At the top of the infographic, we find the main pump station computer that allows plant operators to connect to multiple remote pumping stations distributed throughout a city to control automated equipment, monitor reservoir levels, and acknowledge alarms from a central computer using graphic screens similar to the one shown in this slide. The final products developed for this assignment are a SCADA course outline, sample lecture lesson plan, and summary of laboratory activities for the winter 2017 semester. Research studies were examined to assist in the selection of course learning outcomes and provide frameworks for the design of the laboratory learning environment of this post-secondary SCADA course. SCADaoutline, Jovanovic, Tarjan, and Stankovsky posit there is a need for engineers with knowledge and skills in various areas, including mechanics, machine design, programming, electronics, embedded systems, control, and automation. To support the first course learning outcome discussed on a previous slide, an included sample lesson plan illustrates an in-class activity that requires students to review a case study in a group setting and identify the benefits of upgrading an older water treatment system to a new SCADA software system in Kingston, Ontario. According to Bezaden and Kamat, education in science and computer technology programs need to facilitate activities that connect in-class concepts to real-world applications. The SCADA course will be facilitated face-to-face through 2 hours of laboratory work and 2 lecture hours per week for a 14-week semester. Lecture activities will be designed to support students in their laboratory design work. Knowles' principle of andragogy cites the importance of providing clear instructions, activity motivation, and temporary guidance for adult learners. Supporting the inclusion of a laboratory component, Sahin and Isler found that feedback from the majority of learners in a post-secondary SCADA course study noted the experimental portion of the course to be a key success factor in the development of their knowledge and motivation for the automation discipline. In other literature, SCADaoutline, Jovanovic, Tarjan, and Stankovsky conclude from empirical surveys that after transforming a course from a purely theoretical lecture format to include lab-based activities, student success rates drastically improved. Essential employability outcomes, or soft skills, embedded in the course outline align with a promising collaborative business model identified in research literature as agile principles. When applied to technical education, D'Souza and Rodriguez term these principles as extreme pedagogy, which is founded on the pillars of student participation, goal-oriented instruction, pair-based learning, and frequent assessment. As such, laboratory programming exercises are project-based and learner-centric. The strength of this framework is evident in its goal to adapt successful teamwork strategies from industry to address a cited shortfall in engineering graduates' collaborative working skills. Stemming from Zapater, Malagon, de Goyeneche, and Moya's guidance, group programming exercises will be assigned in pairs to optimize learning potential and avoid situations that can result in a few key students carrying the workload for others. Further to this, formative verbal feedback will be provided to students on a weekly basis to help prepare them for their formal lab demonstrations that typically occur every 2 weeks. As described by Ronan, formative assessments aim to provide students with an indication of how they are proceeding through a learning goal. Shifting our focus from the learning environment to the remaining CLOs, or course learning outcomes, Adamo, Attivissimo, Cavone, and Giaquinto highlight in their seminal article the importance of designing laboratory exercises that allow students to develop applications through a real-world approach. The authors continue in their study to describe that the core of an EMTY program shall relate to programmable logic controllers and SCADA systems, technologies that CLO number 2 and 3 are centered around. Further to this, the software and hardware used by students in our laboratory, as shown in these screenshots, is industrial grade and can be found in real-world automation applications around the globe. It should be noted that in a study relating to the implementation of a laboratory setup for a SCADA course, Sahin, Olmez, and Isler had to utilize smaller-scale microcontrollers for students to program, as the real-world PLCs, or programmable controllers, were cost-prohibitive. Fortunately, the existing laboratory in which our SCADA course will be facilitated already includes industrial-grade PLCs, strengthening the quality of education that our students will experience, connecting educational practice to real-world processes. CLOs number 5 and 6 are informed from research findings that note the importance of including remote access to automated SCADA systems from any computer that has an internet connection. Adamo, Attivissimo, Cavone, and Giaquinto emphasize that with today's technology, it is possible to use a common personal computer in order to implement even complex remote supervisory tasks of simple as well as highly sophisticated industrial plants. Furthermore, recent advancements and flexibility benefits of wireless communications are making their way into new automation systems. Thus, to keep our graduates at pace with advancements in industry, this SCADA course includes activities for learners to apply wireless technologies for remote alarm monitoring of laboratory equipment. Moving forward, Albert, in 2014, cited the importance of improving the awareness, knowledge base, and programming skill set of SCADA system designers through post-secondary education in order to protect industrial SCADA systems from potential cybersecurity threats. Serving this need, programming activities found in laboratory exercises numbers 4, 5, and 6 incorporate concepts contained within CLOs number 4, 7, and 8, which require students to create various user login and password protection policies in their projects. Depending on the function of the user, different system controls will be available. For example, an instrumentation technologist will be able to manipulate and control all parts of the SCADA system from a remote location. Yet a business manager will primarily have access to monitor the system and print logged data reports like the sample shown here. Satencevez and Binder underscore the importance of building SCADA applications with levels of password protection in order to prevent unauthorized users from accessing secure system data. In this presentation, I have provided an overview of how research has informed curriculum decisions made in the development of a SCADA course outline. Frameworks from research studies have also contributed to the design of a project-based laboratory learning environment for third-year EMTY students. Thank you for viewing this presentation, and I look forward to discussing this presentation further with you back in Adobe Connect.